Hello Victory students, this is Mr. Duncan. This is a video over section 8-1. This is about the geometric mean, and specifically folks, the focus we are looking at is using similar triangles to create proportions. So the first theorem 8-1 should feel very familiar to you. All we're starting off with is a right triangle, and we're going to drop an altitude from point C. So now we have length CD. This is now an altitude. Theorem 8-1 says if you drop an altitude from point C, we now get three right triangles, and we should be able to show that these three right triangles are in fact all similar. And so first of all, I'm going to mark this angle. I'm going to call it a 30-degree angle just to give it a number. Well, that means that angle A, this angle here, should be a 60-degree angle because these angles must be complementary in order to add up to 180 with the 90-degree angle there. So these three angles should add up to 180 degrees, meaning these two angles in a right triangle should add up to 90 degrees. So that's 30, this must be 60. Okay, great. Look also now at triangle CDB. You'll see that this angle must also be 60 degrees because 30 plus 60 is 90 here, and that's a 90-degree angle. So we have 30 plus 60 is 90 plus another 90 is 180 degrees. You should now be able to see that we have congruent angles here and congruent angles here. So by angle-angle similarity, these two triangles are congruent. Therefore, this angle will be 30 degrees as well. We now have enough information to show that the small triangle, its angles are congruent to the medium triangle's angles, which is also congruent to this large triangle's angles. We can therefore conclude that if CD is an altitude to this triangle, then we are going to get three similar triangles. So triangle ABC will be similar to triangle, let's see here, on the other triangle, that would be triangle CBD. Order here, of course, is incredibly important so that our angles correspond in the right order. And last, we will use triangle ACD. So, folks, if these three triangles are similar, that means their sides are proportional, so we can set up proportions to solve for their side lengths. What makes them so unique is that these side lengths are getting used by multiple triangles. So I'm going to be referring to the small triangle, the medium triangle, and the large triangle from here on out. I'm also going to refer to their side lengths informally as the short side, the long side, and the hypotenuse. It won't always be clear which side is the short or the long or the hypotenuse, but for our purposes it makes it easy to reference pieces. So we'll notice that on these three triangles, some of their parts are interchangeably used. On the small triangle here, we see that this side length, CA, is the hypotenuse. On the medium triangle, that would correspond to side length CB. This is the hypotenuse of triangle CBD. On the large triangle, the hypotenuse is length AB. So those three sides are going to correspond to each other between these three triangles. Now, we're going to see when we compare those ratios and we make a proportion that we get this interesting phenomenon, which we are going to later call the geometric mean. Algebraically, we define the geometric mean using this proportion, where A and B are two numbers. We call these numbers, of course, our extremes. You will remember this from earlier notes, probably in chapter 7. And we will call the x's our means. In order to solve a problem like this, you would cross multiply. You're going to get x squared is equal to a times b. In order to solve that, we would need to find the inverse of squaring something. The opposite of squaring something is not, I repeat, not dividing by 2. Instead, we are going to take the square root on both sides. So we will get that x is equal to the square root of a times b. Now, I want to talk to you about why we call this x value the geometric mean of these two numbers. To do so, I want you to recall what the arithmetic mean is. You should have learned that probably in 7th or 8th grade. The arithmetic mean is also called the average. Well, how do you find the average of a set of numbers? Well, you add them up, and then you divide by the number of numbers you had to add up. So if we only had two numbers, we'd add two of them together and then divide by 2 because there's only two quantities. This is how you find the average. My question to you is, what does the average look like in reference to these two numbers, though? To demonstrate this, I'm going to put two numbers here on our number line, and we're going to find the arithmetic mean of 2 and 8. So if I add 2 and 8, I get 10. Divide that by 2, and I end up with the value 5. So I'll put 5 up here, excuse me. Now, here's what's so interesting about the number 5. It is exactly 3 units, so plus 3 units away from 2, and it's exactly 3 units away from 8. So it has a additive distance that is equidistant from the 2 points it started with. 5 is a measure of center of 2 and 8. So we can see that the average or arithmetic mean gives us a number that is a measure of center between 2 values or more values. Now, when we look at the geometric mean, instead of adding 2 numbers and dividing, we are multiplying 2 numbers and taking the square root. So let's see if the geometric mean has a similar property where it's some sort of center, a measure of center. So I'm going to use 2 and 8 again. This time I'm going to use this formula, a over x equals x over b, to figure out what the geometric mean is between these 2 extremes. So we have 2 over x equals x over 8. We then cross multiply, and we end up with x squared equals 2 times 8 is 16. Therefore, x must equal 4. So the geometric mean is at 4. So if I count that off, 2, 3, 4, 5, 6, 7, 8. So 4 would be right here. Now, looking at that, 4 doesn't feel like it's the center the way 5 is. However, what would you have to multiply 2 by in order to get to 4? Well, you'd have to multiply by 2. And to get from 4 to 8, we would have to also multiply by 2. So if you notice, 4 is a center. It is equidistant from these 2 quantities in a multiplicative sense. We would have to multiply or divide by the same number to get to this number that is multiplicatively at the center of these 2 values. So the geometric mean should feel like the arithmetic mean in this way. Here we see that they are the same distance inward in an additive sense. 4 is equidistant from these 2 numbers in a multiplicative sense. So this is an algebraic definition for what the geometric mean is. We are going to see the same proportion show up when we compare the ratios of these 3 triangles, and we're going to do that down below. We're going to use the same picture as before. We are going to make a triangle, A, B, C, and we're going to drop an altitude down in it. So please label that the same, and I will pause the video to do so.